welcome our next speaker, Renato, who will talk about simulation by meta-converse.
Great. Hello, everyone. So my name is Dr. Michael Shunsao, and welcome to my talk. And today I'm going to present a joint work with Mario, Haochong, Omar, Adil, and Yongshen. It's very interesting that all of these guys are here. Yeah, so the topic is on the error exponent of and strong converse exponent of channel simulation. But what is more interesting is that we would like to show that the meta-converse approach when solving this problem is tight. And what is even more interesting is that we want to show why that meta-converse in terms of error exponent is tight, and we hope that this can motivate further studies in other problems. So before, does this work? No.
I think it's closed.
Oh.
Check on the side.
I can simply stand here.
Maybe
Okay, that's fine. I'll just move a little bit less. So, yep, great. Now I can move around. So, before I start talking about this problem, I would like to give us some motivations. I know that almost all of you are information theorists. So a fundamental problem of information theory is to study the value of a channel in terms of communication. I mean, how resourceful it is. And to do that, we would like to compare channels with each other, right? So what we want to know is that whether when we do the comparison, is the value or worthiness of a certain channel kind of fixed, regardless of which channel you are comparing it with, so that we can have a static world view, or that is just just not nonsense, and the value is actually dynamic. So that's why we need to do channel interconversion, and we would like to ask that how difficult it is to convert one channel from to another. So the question is like to ask whether it is possible to create m copies of channel, say W, from n copies of channel V, when we have some tolerance or approximation parameter epsilon. So say, okay, this is an illustration. Say we have the y-axis and x-axis as the kind of the resources or the resultant resources we would like to have. And the darker it is, the smaller error it is, and the more concrete we feel that such conversion is possible. So we would like to study how this graph will look like. In a situation when the target channel is the perfect channel, this problem has been long solved. It's known as the channel coding. And we know that, roughly speaking, this graph will have a phase transition along the slope line of the capacity. When it's like when it's over capacity, we simply cannot send that many bits. So when the resource channel is a perfect channel, and this problem is known as the channel simulation problem, and we know that the slope became the inverse of the capacity. So both these questions in this kind of extreme cases has been answered in the first order asymptotic regime. Then by combining these two results, we know that roughly speaking, when we do the channel interconversion, we have a kind of slope that is the ratio between the channel capacities. And so that sounds like pretty good, right? So channel interconversion is solved in first order, especially in this case with shared resources as assistance. However, we would like to have finer results. We would like to know that if if the block length n is not that large or it grows slowly, whether this kind of phenomenon is still kind of a simple combination of what is already known for the channel simulation and channel coding, which is now known. For star tests, we can have multiple cuts to look at this kind of diagram as n grows larger and larger. For one, we can consider the situation that we have fixed distortion or fixed error. Then we'd like to ask how large the resource needs to grow, how fast the resource needs to grow as the block length grows. And the other type of questions is that we can ask that for fixed error and for fixed rate, and how fast the error or the distortion will either tends to 1 or 0, and that's known as the error exponent or strong converse exponent. And for this graph, that is kind of looks like, do we have laser here? Yes. That looks like kind of inverse of the channel coding graph. For that one, you will look something like that, the other way around. This is for the channel simulation. So to answer the kind of second order result survey of channel interconversion, the first step is to answer the second order channel coding that is already done. The second step is to answer second order channel simulation that was done like a few years ago. And then we also need to answer, say, error exponent and strong converse exponent for channel simulation. And that is what today's talk is for. Yeah, strong converse exponent. Then one way to study this is to go through the one-shot approach, where we only look at, say, a single copy of the channel, or in this case, a single copy of the target channel for channel simulation. Then we ask the number of resource channel we need, and roughly we have a pretty nice expression for the amount of bits or the amount of binary perfect channel we needs like this. That can be characterized roughly by the partial smooth max information of a channel. Then also then what we do is to apply this one-shot results to n-fold of the channels and see how it grows. Of course, this will recover the first order results, recover the reverse Shannon theorem. Then to study the error exponent, we apply this method to, again, this one-shot method to the channel simulation, but in this case, we look at the minimal deviation, like this. So we have the problem, or this is all possible synthesized channels given certain resource channels, say size of n. Then we would like to ask what is the minimal distortion that is ever achievable. And then that gives us one shot, and we hope to analyze that in the large deviation regime. The first thing is like, we don't know how to analyze this. We can write this out, and it looks like pretty ugly, and looks like a huge optimization problem. In particular, we have a shear randomness that is supposed to make the problem easier, but this shear randomness, we never really bound its size. It's potentially a continuous random variable. So one way to solve this problem is to go through the so-called meta-converse, where we relax this problem as a linear program, and which is directly related to the non-signaling resources in physics, which this line is directly related, as is effectively a rewritten of the non-signaling resource, where we require the joint encoding decoding map to be non-signaling. So, of course, by meta-converse, we know that this is relaxation. We know this area is going to be smaller because we have more resources here, and that is simple. But not the other side, not the other way around. So we would like to ask how far away are these two programs? How much we messed up when we replace the shear randomness by non-signaling resource? And the answer is not that much. Okay, if you do a second order analysis, it's still a lot. So, but for large deviation analysis, is okay. The idea is like for any feasible solution that used non-signaling, we can cook up a sheer randomness assisted protocol that is not terribly far away. By saying not terribly far away is saying that we want this number to be as close to 1 as possible, right? If this is as close to 1, that, I mean, they are both conditional distributions, they have to be exactly the same. The way this is done is to construct this sheer randomness protocol where rejection sampling from m prime copies of sheer random variables, where each sheer random variable is derived from the this auxiliary variable from the non-signaling program. Okay, the details is like this. I'm not sure whether I want to dive into. Wait, why is it moving? Wait, oh, okay. Okay, and details is like this. I'm not exactly sure whether I want to dive into the details. We have the sheer random variables, and we do rejection sampling. And that this expression is exactly the probability that rejection sampling is successful. So which is like the cookup protocol is exactly the same as the non-signaling with this probability, and with 1 minus this number, then it is something else, and we don't really care what that something else is, and that's how it works. So what is the implication if we can cook up a sheer randomness protocol like this? The implication is that, okay, for starters, we can let m and m prime be the same. Then this can be lower bounded by 1 minus 1 over e, which is a fixed number. Then I'll plug it in back to the original two programs, and we can immediately see that the success probability, or 1 minus the duration, their ratio is lower bounded by 1 minus 1 over e, which is a number, right? Because when we study the exponents, we would like to take log of them. When we take log of them, that means that they are off by something like 3 bits. Then we divide it by n, 3 over n tends to 0. So that's why we are happy, even if this kind of looks ugly. Yeah, we would like to, okay, we would like this to be very close to 1 if we are doing small error analysis, small deviation analysis, but for large error, large deviation, we're happy. Is it slow or not working? Oh, okay, it is slow. Then, by the same argument I just said, by letting n tends to infinity, we know that the simulation capacity under sheer randomness is exactly the same as simulation capacity under non-signaling. And as entanglement assistance is a resource that is kind of bounded between these kind of resources, we automatically have that the entanglement assisted simulation capacity is also exactly the same. And a third implication is exactly what I said. They are going to have exactly the same error exponent, the non-signaling one and the shared randomness one. Also, they are going to have exactly the same strong converse exponent. That allows us, instead of considering that very ugly program with n at the beginning, we can directly look at the non-signaling distortion, say in this case is total variation distance. And we can show that under non-signaling it can be nicely expressed like this, which has a closed form expression. Then we apply this to unfold on the channels and let the size of the perfect channel goes exponentially, like e to the power nr, which means rate is r. And we plug it in, and we run a whole bunch of analysis. We can show that the error exponent can eventually be expressed in terms of the alpha running divergence. That's for error exponents. Similarly, for strong converse exponents, we have an expression that looks like this. by following similar arguments. Where, yes, I already mentioned where I alpha is the channel mean tree information of order alpha. So, CQ channels, where we again consider this relaxation of the original program as a SDP program, which is nothing but the non-signaling resource relaxation, which we rewrite as P in this, pi as in this case. Again, we ask the question, how far away are these two programs? And again, we have very similar results like the previous slides. And with the main, okay, actually I didn't write it down. With the main changes is that originally we used rejection sampling, right? But in this case, we have one side of the system being classical and the other side being quantum. And we are using coherent rejection sampling. And all we need is a Woman theorem to ensure that a isometry exists. So which is not conceptually, which is not terribly different from rejection sampling in this case. So
it should be entanglement.
I think so. Actually, I'm not terribly sure. Yeah, I think it's entanglement assistant. Even in the end, that for part of the system, we actually only need classical shared randomness, and we kind of signal that part using entanglement assistance, but we also need entanglement assistance at the very beginning. Okay, and we have similar results, which means that we can do the analysis of the error exponent analysis directly on the non-signaling distortion for CQ channel simulation. And in this case, we are doing the pure distance. We are considered pure distance, which have a nice closed form expression like this. Apply that to unfold, run a whole bunch of analysis. We have an expression in terms of the sandwiched Renner divergence. And similar story holds for the strong converse exponents in this case. Okay, am I being terribly fast? When did I even start? Like, that's 15 or 20. I started at 20. Oh, I'm not being terribly fast. So today, so what we have done is to fill the gap of channel simulation for fixed rate and consider how the duration changes as n grows larger and larger. We have shown that the error exponent and strong converse exponent under the classical channel simulation and also classical quantum channel simulation. So the basic idea of what we did is like we start with the one-shot channel simulation of the using non-signaling resource. And we kind of, as a relaxation of the shear randomness one or the entanglement assisted one, then we have the rounding result is this. That's what that showed. That's showing that they are not terribly far away from each other. Then we consider the error exponent and strong converse exponent of the non-signaling case, and then we can use that directly as the error exponents and strong converse exponents for the target ones. Similar stories for the CQ channel simulation. We actually also did some work on the QQ channel ones, but the rejection sampling doesn't actually directly work in that case because the input system became quantum. Is this no? Wait, am I going backwards of? Okay, yes. So yes, that is one for the QQ one. And in this case, one need to use convex split lemma, which will give us slightly worse results compared to rejection sampling. And that kind of destroys the equivalence of the error exponents. I just mentioned that. It's not what I want to emphasize. So I think we have a lot of time for questions. I hope.
for the talk. That was an unexpected end. Let's hope we have many questions.
Well, if you don't have questions, then we have to wait for the coffee break.
It's fine. There seems to be at least one.
Thanks for the cool talk. Thanks for the cool talk. This is sort of, at one point you made this point that it's not clear that the shared randomness can even be finite. So there's no results saying there's a cardinality bound for the shared randomness necessary? Like it doesn't show up in your proof methods, but
well,
it's surprising.
I didn't directly look into whether there's a cardinality bound in this scenario, but I do know that there are cardinality bounds for other problems, especially for Mac channel simulation. Is Aditya here?
I mean, there are cardinality bounds.
Okay,
You can
there.
even do the trade-off between shared randomness versus communication costs and stuff like that.
Okay, cool. Thank you.
Is there a critical rate for the error exponent?
No, okay, yeah, you asked me to mention that multiple times, yeah. Yeah, as a main selling point, and I have my boss sitting there, and I'm not selling things hard enough. Yeah, I guess I'm not losing my job. No, there's not. That's why this expression looks nice. Wait.
So you're paying attention up to. That's it.
Yeah, thanks for a nice talk. In the QQ channel case, can you go to that slide? Do you have any partial results?
Yes.
Some bounds for the exponent?
Yes, we have the success rate, or 1 minus the deviation that are there in the entanglement assisted one and the non-circulating one. They are related like that. Like that.
So this is first order, and how about the exponent?
Yes, just for the yes, that is for the we have that we have the exponents upper and lower bounds, but it's not. I don't think it's tight in this case. This is awfully detailed, unnecessary. Yes, yes, we have. Oh yes, we have the non-circulating one. That is, I think, is tight, but the relationship between the non-circulating one and the entanglement assisted one is not.
Okay, and then you mentioned you use the convex splitting.
Yes.
But then for the converse,
For the converse, you don't need that. I mean, converse is automatic, right? So one side is smaller than the other.
okay, I see.
Yes,
I see,
because
yeah.
because this is a relaxation, and this one is always going to be smaller or equal to the entanglement assisted one.
So you basically have an exponent from the non-singling.
Yes, yes.
Okay, thanks.
All right, anyone else?
Any more questions?
Questions?
I think the coffee break guy said he would like to have more time at a certain point.
Well, it seems there are no more questions, and let's hope all the co-authors are happy now.